This video tutorial is for mass spectrometry imaging data preprocessing. The user interface consists of three main sections: the user guide, parameter section, and results section. The user guide provides a concise overview of this module. You can configure the parameters in the input parameter section and obtain results from the results section. There are 4 steps for MSI data preprocessing. The first step is to read the MSI data. To proceed, click the plus symbol to expand and access the parameter panel and result panel. Currently, ShinyCardinal supports the IMZML format for MSI data. 2 approaches are available for reading MSI data. The first approach is to read the MSI data locally, directly from your computer. The second approach requires you to upload the MSI data files, which will then be read and processed. If you are using ShinyCardinal locally, we highly recommend using the first approach of reading MSI data. This approach is considerably faster, especially when dealing with large MSI datasets. If you are using the web version of ShinyCardinal, you will have to use the second approach for reading MSI data. This approach is suitable for both online and local usage. However, please note that for large MSI datasets, this approach may be slower compared to the first approach. Now I will demonstrate both approaches. In the first approach, you will need to select the folder where the IMZML and IBD files are stored. If you have multiple files, ensure that you place them all in the same folder before selecting the folder. For the second approach, you are required to upload both the IMZML and IBD files. If you have multiple files, make sure to upload all of them in order to process them collectively. Next, you will need to select the MSI data type, either high mass resolution data or low mass resolution data, and specify the appropriate mass resolution accordingly. If you know the mass range or wish to trim the data, you can enable the Set Mass Range option and specify the desired mass range. If you don't know the exact mass range of your data, you can simply skip these 2 parameters. If you have multiple MSI datasets with unknown or different data modes, you will need to select a data mode, such as profile mode or centroid mode. Otherwise, you can skip this parameter. Next, you can click the Load Data button to initiate the data reading process. Please note that if you have already defined the mass range, the reading process will be faster. Once the data is successfully loaded, you can click the minus symbol to collapse or close the input parameter and result panel. This will help save space and provide a more streamlined view of the interface. The second step is to calculate mean spectrum of the MSI data, which will be used for an efficient peak picking later on. To proceed, click the plus symbol to expand and access the parameter panel and result panel. There are 2 parameters for this step, and both are optional. The first parameter allows you to subset the MSI data by selecting every nth pixel. This feature is particularly useful when working with large MSI datasets, as calculating the mean spectrum using the entire dataset can be time-consuming. For instance, by selecting every second pixel, that is 1, 3, 5, 7, etc., you can achieve a 2-fold increase in processing speed. Similarly, selecting every 10th pixel will result in a 10-fold increase in speed. It is important to note that setting a larger value for n may lead to the loss of highly localized mass features. Therefore, it is advisable to strike a balance between processing speed and the preservation of important mass features when determining the value for n. If you are unsure, just use n equals to 1 without subsetting your MSI data. The second parameter is the number of workers, which is used for parallel computation to enhance processing speed. If you use ShinyCardinal locally, it is crucial to be aware of the number of cores available on your PC in order to set the appropriate value for this parameter. By using multiple workers, tasks can be executed concurrently, resulting in improved computational efficiency. Then, you can click the Calculate button to calculate the mean spectrum. Note that it might be time-consuming in this step, particularly for high mass resolution and high spatial resolution MSI data. Just be patient. Once this step is finished, you can hover your mouse over the spectrum to inspect and explore it in detail. You can leave the result panel open as you may need it later. To continue, the third step is to calculate the reference peaks. This step contains three specific parameters: the peak picking method, the signal-to-noise ratio, and the peak alignment tolerance. How do you determine the best parameters for this step? Since this step is fast, you can change different parameters and compare the resulting reference spectrum with the mean spectrum. By doing so, you can select the most suitable parameters based on the comparison. For example, let's consider the peak 478.33 in the mean spectrum, which exhibits two isotope peaks. In this case, you can compare this peak with the same peak in the reference spectrum to determine whether the peak and its isotope peaks can still be detected. To illustrate, let's assume I choose the mean absolute deviation noise as the peak picking method, set the signal-to-noise ratio to 50, and the mass alignment tolerance to 10 in the peak picking tab. After clicking the Calculate button, a reference spectrum is generated, which consists of a total of 213 features. Next, I examine the peak 478.33 in the generated reference spectrum. You can see that the peak only exhibits one isotope peak, indicating that the parameters chosen may not be optimized. So, I adjust the signal-to-noise ratio to 10, and recalculate the reference spectrum. You can see that both of its isotope peaks are now successfully detected, and there are 462 features in total. Using the same approach, I can adjust the remaining two parameters, the peak picking method and the peak alignment tolerance. Once I am satisfied with the overall outcome and the detection of desired peaks, I can proceed to the next step. For more comprehensive explanations and detailed instructions regarding the parameters, I recommend referring to the user manual. It will provide in-depth information and guidance to ensure a better understanding of each parameter and its impact on the process. The last step is to bin the peaks in the full MSI dataset to the reference peaks we detected in the mean spectrum. This step contains four parameters: normalization, spectra smoothing, baseline reduction and peak binning, in which spectra smoothing, baseline reduction are optional. They are more commonly used for time-of-flight MSI data. The first parameter is selecting a normalization method, which can be either total ion current normalization or root mean squared normalization. To apply spectra smoothing, you must enable this option and choose a specific spectra smoothing method. Likewise, to apply baseline reduction, you need to enable this option and select the desired baseline reduction method. During the peak binning step, even for peaks that did not meet the peak picking cutoff criteria in individual spectra, their area under the curve is integrated instead of being assigned a zero intensity value. This approach helps eliminate inaccuracies from the peak detection step, and results in a dataset with minimal zero intensity values. As previously mentioned in the Calculate Mean Spectrum step, The parameter for the number of workers can be adjusted to enable parallel computation, thus improving processing speed. Finally, you can click the Process button to initiate this step. It is crucial to be aware of the time-consuming nature of the data preprocessing step. For instance, processing a time-of-flight MSI dataset with a size of 55 GB might take around 20 minutes, while a particular MSI dataset with a size of 25 GB could require approximately 8 hours to complete the preprocessing stage. Given the significant time cost in the preprocessing module, it is advisable to avoid repeating this step when reanalyzing the same data. To address this, you have the option to save the processed MSI dataset as an RDS file. This file can be conveniently used for future analysis.